The nearest star to our Sun is 4.2 light-years away. At the speed of the fastest spacecraft humanity has ever built, the Parker Solar Probe, traveling at approximately 700,000 kilometers per hour. It would take approximately 6,500 years to reach it. 6,500 years. Our entire recorded history, every civilization, every empire, every war, every scientific discovery, every work of art from the cave paintings of Lascaux to the present moment would fit inside that travel time with room to spare. And Proxima Centauri is our nearest neighbor. The Milky Way is 100,000 light-years across. The Andromeda Galaxy, the nearest large galaxy, is 2.5 million light-years away. The observable universe is 93 billion light-years across. By any conventional measure of travel, the universe is not just large, it is impenetrably, permanently, prohibitively vast. Nothing travels faster than light. And even at the speed of light, the cosmic speed limit, crossing the galaxy takes 100,000 years. Reaching Andromeda takes 2.5 million. The universe, it seems, has made interstellar travel effectively impossible. But the universe may have left a back door, a shortcut, a tunnel through the fabric of space-time itself, connecting two distant points not by traveling the space between them, but by bypassing that space entirely. A wormhole. And here is the extraordinary fact that most people don't know. Wormholes are not science fiction. They are not speculation. They are not the invention of screenwriters or novelists reaching for dramatic plot devices. They are a direct, mathematically rigorous solution to Einstein's equations of general relativity. The same equations that predicted black holes, which we have now photographed. The same equations that predicted gravitational waves, which we have now detected. The same equations that predicted time dilation, which we measure every day in GPS satellites. Einstein's equations permit wormholes to exist. The question, the deep, unresolved, genuinely uncertain question, is whether the universe permits wormholes to exist, whether the physics beyond the equations allows them to form, to survive, and to be traversed. And the answer, when you follow the physics all the way down, is one of the most mind-bending stories in all of science. The story of wormholes begins in 1935. Albert Einstein, by then at the Institute for Advanced Study in Princeton, having fled Nazi Germany 2 years earlier, was working with a young colleague named Einstein-Rosen on a problem in general relativity. They were studying the mathematical structure of black holes. Specifically, they were examining the Schwarzschild solution, the solution to Einstein's field equations that describes the space-time geometry around a non-rotating, uncharged, massive object. The solution that describes the simplest possible black hole. When they analyzed the Schwarzschild geometry carefully, when they traced the mathematical structure of the space-time all the way through the event horizon and beyond, they found something unexpected. The geometry did not simply end at the singularity. It connected to another region of space-time, a mirror region, a second universe, or a second distant part of the same universe connected to the first through a narrow throat, a bridge through space-time. Einstein and Rosen published their finding in 1935. They called it an Einstein-Rosen bridge. Today we call it a wormhole. The concept was not widely discussed at the time. Einstein himself did not think it had any physical significance. He doubted that the mathematical structure corresponded to anything real. The singularities of general relativity were, in his view, a sign that the theory was breaking down, not a sign of actual physical geometry. It was not until 1957 that the term wormhole was coined by the physicist John Wheeler, one of the most creative and unconventional minds in 20th century physics. Wheeler, along with his student Charles Misner, studied the mathematics of Einstein-Rosen bridges in detail and recognized their potential significance. But Wheeler also recognized the problem. The Einstein-Rosen bridge, the wormhole that emerges from the mathematics of the Schwarzschild black hole, is not traversable. It opens and closes so rapidly that nothing, not even light, can pass through it before it pinches off. A wormhole exists in the mathematics, but it exists for an infinitesimally brief moment, long enough to be described by the equations, not long enough for anything to travel through. For a wormhole to be useful, for it to serve as an actual shortcut through spacetime, it would need to be held open, stabilized, prevented from collapsing. And that is where the physics becomes truly extraordinary. In 1988, two physicists at Caltech, Kip Thorne and Michael Morris, published a paper that transformed the study of wormholes from a mathematical curiosity into a serious area of theoretical physics research. Thorne and Morris asked a simple but profound question. Under what conditions would general relativity permit a traversable wormhole, one that stays open long enough for something to pass through? They worked out the mathematics carefully, and they found the answer. For a wormhole to remain open, for the throat not to collapse, the spacetime geometry at the throat must be supported by matter with a very specific property: negative energy density. Not just low energy, not zero energy, negative energy. Matter, or more precisely, a form of energy that has a negative value. Energy that is less than the energy of empty space. This is called exotic matter, and it is unlike anything in ordinary experience. In ordinary matter, the matter made of protons, neutrons, and electrons that makes up everything you have ever seen, the energy density is positive. Mass has positive energy. Light has positive energy. Even the quantum vacuum has positive energy density in most models. Negative energy density, energy less than vacuum, is deeply counterintuitive. And for a long time, physicists assumed it was simply impossible, that the universe did not permit states with negative energy density. But quantum mechanics says otherwise. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged, perfectly conducting parallel plates, placed very close together in vacuum, would experience an attractive force, not because of any classical electromagnetic interaction, but because of quantum vacuum fluctuations. The quantum vacuum is not empty. It seethes with virtual particle-antiparticle pairs constantly popping into existence and annihilating. Between the plates, only vacuum fluctuations with wavelengths shorter than the plate separation are permitted. The geometry constrains them. Outside the plates, all wavelengths are permitted. This asymmetry produces a difference in energy density. The energy density between the plates is lower than the energy density outside, lower than the vacuum. Negative energy density relative to the vacuum. The Casimir effect was predicted in 1948. It was confirmed experimentally in 1997. Negative energy density is real. It exists. It has been measured in a laboratory. But there is a problem. The amounts of negative energy produced by the Casimir effect are extraordinarily small, and the amounts needed to hold open a traversable wormhole are extraordinarily large. Thorne and Morris calculated that a wormhole with a throat 1 meter in diameter would require an amount of exotic matter with negative energy comparable to the mass energy of Jupiter. But negative. Negative Jupiter mass of exotic matter. We have no idea how to produce anything remotely close to this quantity. The Casimir effect produces negative energy in amounts that would require scales to measure, not quantities remotely approaching what a wormhole would need. Whether the required amounts of exotic matter could exist anywhere in the universe, whether quantum gravity effects might permit it, whether some as-yet unknown physics might produce it, is genuinely unknown. This is the fundamental obstacle to traversable wormholes, not the geometry. The geometry works, but the matter required to support the geometry may not exist in the needed quantities. In 1988, two physicists at Caltech, Kip Thorne and Michael Morris, published a paper that transformed the study of wormholes from a mathematical curiosity into a serious area of theoretical physics research. Thorne and Morris asked a simple but profound question. Under what conditions would general relativity permit a traversable wormhole, one that stays open long enough for something to pass through? They worked out the mathematics carefully, and they found the answer. For a wormhole to remain open, for the throat not to collapse, the space-time geometry at the throat must be supported by matter with a very specific property. Negative energy density. Not just low energy, not zero energy, negative energy. Matter, or more precisely a form of energy, that has a negative value. Energy that is less than the energy of empty space. This is called exotic matter, and it is unlike anything in ordinary experience. In ordinary matter, the matter made of protons, neutrons, and electrons that makes up everything you have ever seen, the energy density is positive. Mass has positive energy. Light has positive energy. Even the quantum vacuum has positive energy density in most models. Negative energy density, energy less than vacuum, is deeply counterintuitive. And for a long time, physicists assumed it was simply impossible. That the universe did not permit states with negative energy density. But quantum mechanics says otherwise. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged, perfectly conducting parallel plates, placed very close together in vacuum, would experience an attractive force. Not because of any classical electromagnetic interaction, but because of quantum vacuum fluctuations. The quantum vacuum is not empty. It seethes with virtual particle-antiparticle pairs constantly popping into existence and annihilating. Between the plates, only vacuum fluctuations with wavelengths shorter than the plate separation are permitted. The geometry constrains them. Outside the plates, all wavelengths are permitted. This asymmetry produces a difference in energy density. The energy density between the plates is lower than the energy density outside, lower than the vacuum. Negative energy density relative to the vacuum. The Casimir effect was predicted in 1948. It was confirmed experimentally in 1997. Negative energy density is real. It exists. It has been measured in a laboratory. But there is a problem. The amounts of negative energy produced by the Casimir effect are extraordinarily small, and the amounts needed to hold open a traversable wormhole are extraordinarily large. Thorne and Morris calculated that a wormhole with a throat 1 meter in diameter would require an amount of exotic matter with negative energy comparable to the mass energy of Jupiter, but negative. negative Jupiter mass of exotic matter. We have no idea how to produce anything remotely close to this quantity. The Casimir effect produces negative energy in amounts that would require scales to measure, not quantities remotely approaching what a wormhole would need. Whether the required amounts of exotic matter could exist anywhere in the universe, whether quantum gravity effects might permit it, whether some as yet unknown physics might produce it, is genuinely unknown. This is the fundamental obstacle to traversable wormholes. Not the geometry. The geometry works. But the matter required to support the geometry may not exist in the needed quantities. Here is where wormholes become truly mind-bending. If a traversable wormhole could exist, if exotic matter could hold one open, then with a relatively simple additional step, it could become a time machine. Not science fiction, mathematics. Here is how it works. Take a wormhole with two mouths. Initially, both mouths are at the same location in space and at the same moment in time. They are synchronized. Now take one mouth and accelerate it. Move it at high velocity through space for a period of time, then bring it back. Remember time dilation, the slowing of time for objects moving at high velocity, which we discussed in our video on time. The mouth that was accelerated has experienced less time than the mouth that stayed still. The two mouths are now desynchronized. They exist at different moments in time, but they are still connected by the wormhole throat, which means that the wormhole now connects two different times as well as two different places. Step into one mouth in the present. Emerge from the other mouth in the past. A time machine. Kip Thorne, one of the physicists who worked out the traversable wormhole mathematics, recognized this implication and took it seriously. He published papers on wormhole-based time machines in the late 1980s and early 1990s, not as science fiction, but as serious explorations of what general relativity permits. The possibility of time travel raises immediate paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your own birth, do you exist or not? The logical contradiction seems to rule out time travel entirely. But physicists have proposed resolutions. The Novikov self-consistency principle, proposed by Russian physicist Igor Novikov, states that only self-consistent histories can occur. Any action you take in the past is part of the history that led to your time travel in the first place. You cannot change the past. You can only fulfill it. Stephen Hawking proposed a different resolution, the chronology protection conjecture. He argued that the laws of physics conspire to prevent the formation of closed time-like curves, time travel paths, even when the geometry seemingly permits them. Quantum effects, he suggested, would build up at the moment a wormhole threatened to become a time machine, producing enough energy to destroy the wormhole before it could be used for time travel. The chronology protection conjecture is not proven. It is a conjecture, a reasonable expectation based on physical arguments, not a derived theorem. Whether time travel is possible, whether the universe permits it or prevents it through some deeper physical principle, is genuinely unresolved. But the mathematics says, if traversable wormholes exist, time travel may follow. In 2013, two physicists, Juan Maldacena and Leonard Susskind, published a paper with a title that sounds almost like a mathematical equation. ER equals EPR. ER stands for Einstein-Rosen. The Einstein-Rosen bridge. The wormhole. EPR stands for Einstein-Podolsky-Rosen. a famous 1935 paper by Einstein, Boris Podolsky, and Nathan Rosen, the same Rosen who co-discovered the Einstein-Rosen bridge that described what we now call quantum entanglement. Quantum entanglement is one of the strangest phenomena in physics. When two particles are entangled, when their quantum states are correlated, measuring one particle instantly determines the state of the other, regardless of the distance between them, even if they are on opposite sides of the galaxy, even if they are separated by billions of light years. Einstein called this spooky action at a distance. He was deeply uncomfortable with it. It seemed to violate locality, the principle that nothing can influence anything else faster than light. We now know that entanglement is real. It has been confirmed in experiment after experiment. Particles separated by large distances show correlations that cannot be explained by any local hidden variable theory. But entanglement does not allow faster-than-light communication. The correlations are real, but you cannot use them to send information faster than light. The measurement results are random. You cannot control what you get, so you cannot encode a message in them. Entanglement exists. It is strange. And it connects, in Maldacena and Suskind's conjecture, to wormholes. The ER equals EPR conjecture proposes that entangled particles are connected by a wormhole. Not metaphorically, not as an analogy. Physically. The quantum entanglement between two particles is, in this picture, the same thing as a microscopic wormhole connecting them through space-time. A Planck-scale wormhole, invisibly small, carrying no information, consistent with the prohibition on faster-than-light communication. But real in the sense that the geometry of space-time between entangled particles is connected through a microscopic throat. If ER equals EPR is correct, and it has gained significant traction in theoretical physics, then wormholes are not exotic, rare, hypothetical objects. They are everywhere. Every pair of entangled particles is connected by a microscopic wormhole. Every quantum correlation is a geometric connection. The quantum fabric of reality and the geometric fabric of space-time are, in this picture, the same thing. Space-time itself, the smooth, continuous geometry of the universe at large scales, may emerge from the quantum entanglement of its microscopic constituents. The geometry of the universe is built from wormholes. This conjecture connects two of the deepest mysteries in physics. Quantum entanglement, the non-local correlations of quantum mechanics and space-time geometry, the continuous fabric of general relativity. If it is correct, it suggests that the path to a theory of quantum gravity, the long-sought unification of quantum mechanics and general relativity, runs through wormholes. That understanding wormholes is not just a question about exotic astrophysics. It is a question about the fundamental nature of space and time. Could wormholes form naturally, without any technological intervention, somewhere in the universe? This is a question that theoretical physicists have taken seriously. The most discussed possibility involves the early universe. In the extreme conditions of the Planck era, the first 10 to the power of negative 43 seconds, which we discussed in our Big Bang video, the quantum fluctuations of space-time itself were enormous. Space was not smooth and continuous at the Planck scale. It was a seething, foaming chaos of quantum geometry, a space-time foam, as John Wheeler described it. In this foam, microscopic wormholes may have been constantly forming and collapsing as part of the quantum fluctuations of the geometry itself. Not macroscopic traversable wormholes, but Planck-scale geometric structures, forming and dissolving in the quantum vacuum. Some of these microscopic wormholes might have been inflated to larger sizes during cosmic inflation, the exponential expansion of the early universe. The same process that stretched quantum density fluctuations to cosmic scales might have stretched quantum wormhole fluctuations. Could a macroscopic wormhole have formed in the early universe and survived to the present day? Theoretically possible, practically unknown. We have no observational evidence for any macroscopic wormhole anywhere in the universe. No gravitational lensing signature, no anomalous space-time geometry, no signal from the other side. But absence of evidence is not evidence of absence. The observational signature of a wormhole, what it would look like to telescopes, depends strongly on the wormhole's properties. Some wormholes might look very similar to black holes from the outside. Distinguishing them observationally would require precise measurements of the space-time geometry near the object. Several papers have proposed that certain observed compact objects, including some of the objects whose gravitational wave signals were detected by LIGO, might potentially be wormholes rather than black holes. The gravitational wave echoes that some wormhole models predict. Additional signals following the main merger event have been searched for in LIGO data. No confirmed detection. But the search continues. String theory, the leading candidate for a unified theory of physics, has a rich and complex relationship with wormholes. In string theory, space-time has more than 4 dimensions. The theory requires either 10 or 11 dimensions depending on the version. 4 large dimensions that we experience, and 6 or 7 extra dimensions curled up at scales too small to detect. In these extra dimensions, wormholes appear naturally, not just as solutions to the equations, but as fundamental objects. String theory contains extended objects called D-branes, higher dimensional generalizations of particles and strings, and wormholes in the extra dimensions can connect different branes, potentially allowing shortcuts through the higher dimensional space-time. More importantly, string theory provides a framework, the ADS/CFT correspondence that we mentioned in our black hole video, in which the ER equals EPR conjecture has been studied in detail. In this framework, wormholes in a higher dimensional spacetime correspond precisely to quantum entanglement in a lower dimensional theory. The conjecture is not just a speculation in this context. It is a derived result, at least in the specific setting of the ADS/CFT correspondence. And in 2022, a team of researchers at Caltech used a quantum computer, the Google Sycamore processor, to simulate a wormhole. Not a real wormhole, a quantum simulation, a mathematical model of a wormhole running on a 9-qubit quantum processor. But the simulation demonstrated something important. A quantum teleportation protocol, sending quantum information from one part of the system to another, behaved in a way consistent with the wormhole interpretation. The quantum information appeared to travel through what the researchers described as a traversable wormhole in the quantum simulation. The result was controversial. Some physicists argued that the system was too small and too simple to genuinely demonstrate wormhole physics. Others found the result suggestive and important. But it pointed toward a future in which quantum computers might be used to probe the physics of space-time, including wormholes, in ways that no classical experiment can achieve. Let's say, hypothetically, that a sufficiently advanced civilization wanted to create and use a traversable wormhole. what would it actually require? Setting aside the exotic matter problem, which is the fundamental obstacle, a traversable wormhole faces several additional challenges. The first is stability. Even with exotic matter holding the throat open, a wormhole is an extraordinarily fragile geometric structure. Small perturbations, the presence of any ordinary matter or energy near the throat, can trigger instabilities that cause rapid collapse. Maintaining a stable wormhole against all perturbations would require active control, a continuous supply of exotic matter precisely distributed to counteract every fluctuation. The second is radiation. Any object entering a wormhole would encounter intense radiation near the throat. This radiation arises from quantum effects, the same Hawking-like processes that occur near black hole horizons also occur near wormhole throats. For a wormhole with a macroscopic throat, the radiation might be survivable. For a microscopic wormhole, one with a throat smaller than a meter, the radiation would be lethal. The third is tidal forces. Near the throat of a wormhole, space-time curvature produces tidal forces, differences in gravitational pull across the extent of an object. For a traversable wormhole to be usable, the tidal forces at the throat must be small enough that a human body or any other macroscopic object can pass through without being destroyed. Thorne and Morris showed that traversable wormholes can in principle be designed with arbitrarily small tidal forces, but at the cost of requiring even larger amounts of exotic matter. The fourth challenge is the energy required. Creating a macroscopic wormhole, assuming exotic matter could be assembled, would require energy comparable to the mass energy of a star or more, concentrated in a small region of space with extraordinary precision. No civilization we can currently imagine possesses anything remotely close to this capability. But, and this is important, no law of physics rules it out. The obstacles are engineering obstacles, extraordinary, almost incomprehensible engineering obstacles, but are not fundamental physical impossibilities. A sufficiently advanced civilization, one that has been developing technology for millions or billions of years, that has mastered the manipulation of space-time geometry and quantum fields, might, in principle, be capable of creating and maintaining traversable wormholes. Whether any such civilization exists, whether any civilization has ever reached that level of capability, is a question we discussed in our Great Filter video. The silence of the universe may be telling us something. Wormholes are not just exotic astrophysical objects. They are windows into the nature of space-time itself. The fact that Einstein's equations permit wormholes, that the geometry of space-time allows for connections between distant regions, tells us something profound about the nature of space. Space is not just a container, not just a passive backdrop against which events occur. It is a dynamic, flexible, geometrically rich structure that can bend, curve, stretch, and potentially connect distant points through shortcuts that bypass the intervening distance. We have confirmed this flexibility in multiple ways. Gravitational lensing, the bending of light by massive objects, is confirmed. Gravitational waves, ripples in the fabric of space-time, are confirmed. Time dilation, the slowing of time in gravitational fields and at high velocities, is confirmed. The expansion of the universe, the stretching of space itself, is confirmed. All of these phenomena reflect the dynamic, geometric nature of space-time. Wormholes are the most extreme expression of that geometry. The possibility that two distant regions of space-time can be connected by a throat, That the topology of space can be non-trivially connected is a direct consequence of taking Einstein's geometric picture of gravity seriously. And the ER equals EPR conjecture deepens this further. If wormholes are connected to quantum entanglement, if the quantum correlations between particles are geometrically expressed as wormhole connections, then the geometry of spacetime is not just a classical, smooth structure. It is built from quantum information. Space itself, the arena in which all of physics takes place, is not fundamental. It emerges from something deeper, something quantum, something that involves entanglement and information and the microscopic structure of reality at the Planck scale. Understanding wormholes, whether they exist, how they form, whether they can be traversed, is not just a question about exotic travel. It is a question about the deepest nature of physical reality, about what space is, what time is, what connects distant regions of the universe, about whether the universe has hidden structure, secret connections between apparently separate regions woven into its geometry at every scale. If wormholes exist somewhere in the universe, natural wormholes, formed in the early universe or by some unknown process, how would we find them? This is a question that has moved from purely theoretical speculation to active observational research in recent years. The first approach is gravitational lensing. A wormhole, like any massive compact object, would bend the light of background stars and galaxies. But the lensing pattern of a wormhole is subtly different from that of a black hole or a neutron star. The geometry of a wormhole throat produces a characteristic pattern of light deflection, including the possibility of light from behind the wormhole passing through the throat and emerging on our side. If a wormhole were positioned between us and a dense field of background stars, like the galactic center, the lensing signature might be distinguishable from that of a black hole, given sufficiently precise observations. The Event Horizon Telescope, the network that imaged M87 and Sagittarius A star, has the resolution to potentially detect subtle differences between black hole and wormhole lensing signatures. Future, more sensitive versions of this instrument might be able to distinguish them. The second approach is gravitational waves. When two compact objects merge, as LIGO and Virgo have detected dozens of times, the gravitational wave signal depends on the internal structure of the merging objects. Black holes and wormholes would produce subtly different signals during the merger and its aftermath. In particular, some wormhole models predict gravitational wave echoes, additional bursts of gravitational waves following the main merger signal, produced by gravitational waves bouncing inside the wormhole structure. These echoes would appear as repeated, decaying signals following the main event. Several groups have searched LIGO and Virgo data for such echoes. Some claimed detections have been made, but none has been confirmed at statistical significance sufficient to claim a discovery. The third approach is more speculative. If wormholes are connected to quantum entanglement, if the ER equals EPR conjecture is correct, then there may be quantum signatures of microscopic wormholes that are detectable with sufficiently sensitive quantum experiments. The Caltech quantum computer simulation was a first step in this direction. Future quantum computers, far more powerful than current devices, might be able to simulate wormhole physics with enough fidelity to test the ER equals EPR conjecture directly. None of these searches has yet found a definitive wormhole, but the tools are improving. The searches are becoming more sensitive. and the theoretical framework is becoming clearer. If wormholes exist, we may find them. Perhaps not with current technology, but with the next generation of instruments, more sensitive gravitational wave detectors, higher resolution imaging, more powerful quantum computers, the search is becoming serious. 4.2 light-years. The nearest star, 6,500 years away at our fastest speed. The universe, by conventional physics, is impenetrably vast, a cosmic prison, beautiful beyond description, but sealed against exploration by the speed of light and the crushing distances between everything. And yet, Einstein's equations, the same equations that gave us black holes and gravitational waves and the expanding universe, say something else is possible. A tunnel, a throat, a connection between distant points that bypasses the space between them. A wormhole. Whether it exists, we don't know. Whether it can be stabilized, we don't know. Whether exotic matter in the required quantities is possible, we don't know. Whether any civilization has ever built one, we don't know. But we know this. The mathematics permits it. The geometry of space-time, the fabric of reality itself, has room in it for shortcuts, for connections, for the possibility that the universe is not just a vast, empty expanse of disconnected points, but a richly connected structure, woven together by geometry in ways we are only beginning to understand. And perhaps, if the ER equals EPR conjecture is correct, those connections are not hypothetical, not speculative, not reserved for impossibly advanced civilizations with access to exotic matter. They are already there. Every entangled particle pair, every quantum correlation, every spooky action at a distance that Einstein found so disturbing, all of it geometric, all of it connected, all of it wormholes, microscopic, Planck scale, carrying no information and serving no practical purpose for interstellar travel. But real. The universe is not just connected by the light that travels across it. It may be connected through it. Through tunnels in space-time so small they exist at scales a billion times smaller than an atom. Through quantum correlations that span billions of light-years. Through a geometry so rich and so strange that our everyday intuitions, shaped by life on a single planet, in a single solar system, within a single galaxy, are nowhere near adequate to picture it. The nearest star is 4.2 light-years away, and the universe may be threaded through with shortcuts we haven't learned to use yet.